Hey everyone, thanks for getting started on the application security project, our first project for Intro to InfoSec. I'm Cole, and I'll be going over control hijacking. If you'd like more information on how to use GDB or shellcode and return-oriented programming, please see the other primer videos. All right, before we talk about stack frames, there are a couple of important CPU registers to go over. Registers are small buffers for data on the CPU that are fixed at 64 bits wide for this project and are very quick to access. Some of them also have designated roles. RSP is the stack pointer. Remember that the stack starts at a high memory address and grows down to a low memory address. So RSP points to the top of the current stack frame, which is also the lowest memory address. RBP points to the bottom of your stack frame. Oftentimes, instruction will use offsets from RBP to refer to local variables on the stack and arguments in function calls. RIP is the instruction pointer, which you might know better as the PC or program counter from another class. This points to the next instruction to be sent through the CPU's pipeline. We also have a bunch of scratch registers, which, without going into too much detail, you can think of as temporary storage for whatever the CPU is currently working on. Let's start with an example of calling the foo method from within main. For each thing we add to the stack, we are also moving the stack pointer up to stay at the top of the stack. So, for the stack buildup, the first thing we have to do is save main's local variables on the stack. Next, we put the arguments for foo onto the stack. Then, we add the return address so the CPU knows where to continue execution after returning from foo to main, as well as main's frame pointer so that we can return to the old frame. Now, we shift the current frame pointer, RBP, and we start going through foo. We add the local variable buff1 to the stack above RBP. Since the method is now finished, we tear down and return. For the teardown process, first we pop the local variables, then main's frame pointer, which goes to RBP, then the return address, which goes to RIP and becomes the new instruction to execute, and finally we pop the arguments and reestablish main's local variables. Now let's apply this to illustrate how a buffer overflow works. We have a similar scenario here, where main calls the doSomething function with an argument from the command line, which you can see as AAAA. The doSomething function makes a 128 byte long buffer and copies whatever was supplied from the command line into this buffer using the string copy function. So after main stack frame, we need a new stack frame for doSomething since it's a separate function. Recall from the previous example that when main calls the doSomething function, main needs to push doSomething's arguments onto the stack, then the return address, and finally the old frame pointer. We move the base pointer to where the stack pointer is, making a new stack frame for the doSomething function. Now that we have a new stack frame for doSomething, what we need to do is grow the stack to make space for local variables, specifically this 128 byte buffer. When we say that we grow the stack, this is done by subtracting from the stack pointer, since the stack grows from higher memory addresses to lower memory addresses. And now we are at the stack after the string copy function has run. String copy copies lower memory addresses to higher ones, so we'll copy the arguments from the command line top down. Here, we are just giving the program 4 A's, so they all fit within the stack frame of the doSomething function. But what if we give it a ton of A's, like way more than 128 bytes that the buffer can hold? String copy has no bounds checking. It will simply copy the source to the destination byte by byte until it sees a null byte, since that determines a string in C. Because string copy copies from lower to higher memory addresses, the A's would go out of bounds and beyond doSomething's stack frame. They would keep going towards everything that we previously stored on the stack, which includes the location of main's base pointer as well as the return address. This means that when the doSomething function returns, the CPU will start execution at the address value 0x4141414141 instead of the original return address, because capital A in ASCII is 0x41 in hexadecimal. This implies that we can carefully craft an input to make the doSomething function return to wherever we want. So let's look at how this would be pulled off. Although we have a separate primer for GDB entirely, we'll use a couple of commands in the next few slides, which I'll now showcase. First is disass, which is short for disassemble. If you say disass main, for example, it will show a dump of assembly code for the main function. Next is info-reg, which will dump the values inside all of the registers at a certain point in execution. One of the other most versatile commands is x, which is for dumping the memory. You can use it like this. After the slash, the 64W means give me 64 words, which are 4 bytes of memory each, and the x at the end means to show them in hexadecimal. As a simple example, if you start dumping from address 0, you might get 8 bytes to begin with. But be careful, since it is stored as Little Endian. So address 0 has byte EF, address 1 has byte CD, address 2 has byte AB, and so on. And the end address 7 has the byte 01. There are more instructions for control flow. NI stands for next instruction and runs whatever the next instruction in the current scope. If it's a subroutine, like a function call, it will execute that in its entirety. Then SI stands for step instruction and runs the next instruction in the entire program's control flow. If there's a function call, it will execute each instruction in the subfunction line by line. C is short for continue and makes the CPU crunch instructions until your next breakpoint, which I'll discuss in a minute, or until it reaches the end of the program. R runs the program because the program doesn't start up right away when you launch it with GDB. Super important is being able to interrupt the program with breakpoints, or B for short. You can break on addresses of instructions like this example, and symbols too. So B main will stop execution just before the main function runs. If your program takes arguments over the command line, don't forget the -args flag to GDB. Finally, there's a cheat sheet for all of those. Here's the link. You can also find it in the project spec. So let's take a look at some code. Here we have a secret function that is never called in the code. If we see how the execution goes, we have main taking arguments from the command line, and main calls vulnerable, which makes a 20-byte buffer, and then string copies whatever is on the command line to this buffer. Our goal is to make the execution of the program jump to the secret function instead of returning to main. Here, we'll compile it with a couple of special flags to make debugging this easier for the sake of the project. We can compile it using GCC and debug it with GDB. args here is the name of the program. Before I show you some assembly, it's important to know that x86 has 2 different notations. Throughout the different primer videos, you may see this slide resurface. First is Intel syntax, where registers are just spelled out as RSP or RAX, and operands are ordered destination first. Then there's the AT&T syntax, where registers are prefixed with a %, and immediates, like the 10 in hex, are prefixed by $signs. Its operand ordering is also different, with the source coming first. GDB will defer to Intel. So we'll first disassemble main to find out where the vulnerable function is supposed to return to. Near the bottom, we see a call instruction to the vulnerable function, which means that when the vulnerable function returns, you want to execute the very next instruction that comes in main. This is why the instruction just after the call is the one that we highlighted, red, not the call instruction itself. Now, we can disassemble the vulnerable function to see where the buffer gets allocated. It's tempting to think that because the buffer is 20 bytes long, it should start 20 bytes before the start of the stack frame, because that would make a perfect fit. However, compilers usually allocate some extra space between local variables and the end of the stack frame, which is why we need GDB for the exact number. One instruction that will help during the project is LEA, which stands for Load Effective Address. LEA is kind of like the ampersand operator in C, because instead of putting the data at a given memory address into the destination operand, it will put the memory address itself. So here, the LEA instruction highlighted in red is subtracting 20 in hex, or 32 in decimal, from the frame pointer, and putting that address in the RAX register as the starting offset of the buffer. Let's set a breakpoint at some arbitrary instruction that's still within the vulnerable function, but after the string copy call, so that we can see what happens to the stack. Then we'll run the program with exactly 32 A's, the size of the buffer. And let's see what happens if we dump 120 bytes of memory in hexadecimal, starting from the stack pointer. Here's the resulting memory. As we go down the lines, we can see that the memory addresses increase. However, because the stack grows from higher to lower memory addresses, we need to go bottom up to go towards the top of the stack. First, we'll outline where the stack pointer is pointing to. So the stack pointer points to the top of the stack because we were doing GDB at x120 bytes, x $SP. So this indicates that this is the start of the memory dump, and the base pointer is here. We can get this information with the info-reg command, which, as you might remember, dumps register values. We can see that where the base pointer is at is 8 bytes, representing the main function's base pointer location. Right after that, we see the return address, but x86 is little endian when we go byte by byte. So we'll see the bytes return right to left. The last byte, 3C, has a lower memory address, while the first byte, 00, has the highest memory address. If you remember the LEA instruction and how it subtracted 20 in hexadecimal, or 32 in decimal from the base pointer, this is indeed exactly where the array starts at, and we see 32 bytes with the value 41 in hex, because again, 41 is the ASCII value for capital A. At this point, we want to write mini A's, or garbage, that would go past the 32 byte buffer and override the stack all the way to where the main's old base pointer value is stored. Then we want the return address to be overwritten with the address of the first instruction of our secret function, so that execution jumps to the secret function instead of main. We can find the address by using the p, or print command, on secret function. That brings us to our exploit payload. We first want to override the buffer all the way up to and including the base pointer. Then we'll take the 20 offset, which is 32 in decimal, and add 8 bytes, since that's how long the old base pointer value is. That's where the 40 bytes of garbage comes from, 32 plus 8. Next comes the bytes that we will use to override the return address. To that aim, we need to convert the starting address of the secret function to little endian, which is what we use the 2 bytes function in Python for. And that's it. If we call the program on that payload, the secret function will run despite never having been called in the original code. Thanks for watching, and have fun on the project.